All right. So like I was saying, I want to talk some about these linear differential equations first. Um, so I guess to start out with, does anyone have any questions right away that they want to ask? All right. So we're sort of talking about these types of equations. So let me just kind of review a little bit. So these are linear equations we're going to talk about. They're linear, and we know they're linear because we see that the y and the dy dx are only multiplied by things related to x and then added together. So there's no multiplying of y with y or the derivatives of y. We're not doing anything nonlinear with respect to y. Okay, so that means it's linear. It's also first order because our highest derivative is a first order equation right here. Okay. Um, so that makes this type of equation a linear first order differential equation. Okay. And so the only way we know how to solve equations so far is separation of variables. And so we look at this equation here, you might try and do separation of variables, but it turns out as long as this g here is non-zero, we can't do separation of variables. Okay, there's no way to get these y's together without without mixing up the x's. Okay, so we're gonna have to do something different for this type of equation besides differential equations, besides separation of variables. But if g was zero, you could do separation of variables, and that's perfectly fine to do. Okay, so oftentimes what we'll do is we'll divide through by a1, whatever's in front of the dy dx, and change it into this form here. Okay, so this is sometimes called the standard form. All right, and so we need to we want to solve this equation. Okay, we can't do separation of variables, and so what are we going to do? So looking at this top equation here, one thing that maybe you're reminded of is the product rule. Okay, it's because we have a dy dx, something times dy dx plus something else times y. So let me remind you, if we had something like f of x times y, and we wanted to do the derivative of that, so we derivative with respect to x of this, we'd have to use the product rule. Okay, and so that would turn into, we leave f of x, we have dy dx, plus, then we do the derivative of f, and we leave y. Okay, so we compare this with this top part here, we see that it looks kind of similar. We have a dy dx, we have a y. If this a0 here was the derivative of a1, we could rewrite that as a derivative of a product. Okay, so we could do that. So if that was the case, you could write this as something like, so if a1 derivative equals a0, you could rewrite that as the derivative with respect to x of a1 times y. Okay, a1 of x times y. All right, and so once the derivative's on the outside, that makes it easy to solve this equation because we know how to undo derivatives. When the derivative's on the outside, we can integrate, or we can do the antiderivative, and that'll undo the derivative, and then we can solve for y. Okay, so that's kind of what we want to do. So problem is, this is not generally the case. Okay, the derivative of a1 normally isn't a0. Okay, that's just not normally how it works out. So what do? We want to be able to get it so that this is true. Okay, and what we find out is if we multiply by something called the integrating factor, shown here, if we multiply that to the second equation, we can actually turn it into something that looks like this. Okay, so if we multiply by mu, this equation here by mu, it turns into something that looks like this product rule right here. And then we can go backwards, pull the derivative out, and then integrate to cancel it out. Okay, so you can kind of see that here. So I won't go too much into how you find that out, but basically you can think about this as e to the antiderivative of p. Okay, so if you were to do the derivative of mu, we know we would have to do chain rule. And so we would have e to the antiderivative of p, but then we would multiply by the derivative of the exponent, which was just p, because the derivative and the integrals will cancel out. And so you get if you multiply through this second equation here by mu, you get mu dy dx plus p of x mu of x y, okay, equals mu times g. Okay, and we see that the derivative of mu is p times mu, and so this turns into exactly what I was wanting before. Okay, this is exactly this form here of the product. Okay, and that means we could rewrite this as the derivative with respect to x of mu times y. Okay, because the derivative of mu is p times mu. Okay, that's just how we created this integrating factor. Okay, and so you could check that if you wanted, but. And so when we're trying to solve first order linear differential equations, basically it just comes down to finding this mu, this integrating factor, and then we can rewrite the equation like this: d dx mu y equals mu times g. Okay, and once it's in here, you can integrate both sides to cancel out this derivative, and then divide by mu to solve for y. All right, so let's see how that works in an example. Okay. If you have any questions, feel free to just use the raise hand function. I think that should notify me. All right, so we have an equation here. We have a first derivative, we have just a y, and we have things multiplying in front of them. The first step is actually we need to get into the standard form here, okay, because we need to figure out what p is in order to find the integrating factor. And so what does that mean? That means we're going to divide through by x squared here. So if I divide by x squared, I have y prime plus x over x squared, x plus 2 equals e to the x divided by x squared. All right, so this function right here in front of the y is our p. And so, you can cancel out one of these x's, it will cancel out with one of these x's below here. And so we have x plus 2 over x. Okay, and so our integrating factor, mu, is e, the antiderivative of p. Okay, so I like to kind of do this in steps. So first, let's find the antiderivative of p with respect to x. And so that becomes the antiderivative of x plus 2 over x dx. All right. So first, this is not exactly what we can do, but we realize there's only a single thing here in the denominator. We can actually split this into two fractions. Just because this is in the denominator, you can't do it the opposite way, but because there's only a single thing in the denominator, we can split it. So this becomes the integral of x over x is just 1 plus 2 over x dx. Okay. And then going through this, the antiderivative of 1 is x, and the antiderivative of 2 over x is going to be 2 natural log of x. All right. And we don't need to include a plus c in this case here. Okay, we're just trying to find some antiderivative of p. Okay. If you added a constant here, it wouldn't matter. It would just kind of get canceled out at the end. Okay. So we don't need a plus c in this case. So that's our antiderivative, and so our integrating factor then mu is e to that. So let's kind of see, it'd be e to the x plus 2 natural log of x. All right, let's try and simplify this. So I see an e and a natural log here. Whenever you see a natural log in the exponent of an e, you should immediately want to try and do something about that. Okay, because those things should maybe cancel out eventually. So we can rewrite that. So an addition in the exponent turns into a multiplication. So this is like e to the x times e to the 2 natural log of x. And then we want it to e to the ln. So we can use our log rules, and we can move this 2 into the exponent of the x. So this is like e to the x e to the natural log of x squared. And now the e and the natural log cancel. And so this is like x squared e to the x. All right. So that's our integrating factor, x squared e to the x. And so we know if we multiply through our differential equation, it'll turn into this product rule form. Okay, so we multiply this mu to this differential equation right here. What would we get? So let me just kind of show this in detail. So we'd have x squared e to the x times y prime plus x squared e to the x times x plus 2 over x times y equals x squared e to the x e to the x divided by x squared. All right, so basically what we know is that this left-hand side right here, by the way we created mu, has to look like this. It's basically the derivative of x squared e to the x, our integrating factor, times y. Okay, so you could check that if you worked out the derivative of this, it would turn into this left-hand side right here. Okay, but we know by the way we created mu that that's true. Okay, and so in practice you could just skip right to here, to this part right here. Okay, because we know this is how it's going to work out. And then we have to our right-hand side is mu times whatever was there before. Okay, in this case, some nice things happen. We get the x squareds cancel. E to the x is really e to the 2x. Okay, so that's not too bad. All right, so we get to here, and we realize, well, we need to cancel out this derivative. Okay, and we cancel out derivatives by integrating. So we integrate with that side with respect to x, which means I also need to integrate this side with respect to x. Okay, so the derivative and integral cancel. We're left with x squared e to the x times y. And then we have to do the antiderivative of e to the 2x. Okay, so e to the x, the antiderivative is e to the x, but we have a 2 in here, so that's going to put a 1/2 out front. Let me do the antiderivative. Okay, and so you could check that with like a substitution, u equals 2x, and then you'd get this 1/2 factor out front. Let me move that up here. Okay. All right, and in this case, we do need to include a plus c. All right. Because we're trying to do the general antiderivative here. When doing the integrating factor, mu, we just needed any antiderivative of p in the exponent. Okay, which means we can pick c to be 0, and we can just ignore it. But here, we're doing a general antiderivative, and that means we need to include a constant. Right, and so the last step then is just solve for y, divide that x squared e to the x across. And so you have 1/2, 1 over x squared e to the 2x divided by e to the x is going to be just e to the x. And then we have plus c over x squared e to the x. Okay, so that's our solution to the differential equation. It's general solution because we have a constant c here. Okay, so I did a few extra steps here. In practice, what you could do is you could just kind of use this formula here. So once we find mu, x squared e to the x, basically we know right away that y is going to be 1 over mu times the integral or the antiderivative of mu times g of x. Okay, whatever was there before. Okay, so you could just basically find mu and then just plug it into this formula right here, find the antiderivative, simplify the dividing, and you'll pop out with the same answer here. Okay, but in that's the whole process each time. So we're multiplying by the integrating factor, okay, which puts it in this form. And we recognize that this is actually a product rule. So basically, we're undoing the product rule. So this brings the derivative out front, cancel it with the antiderivative, and then we divide this mu term across to solve for y. All right, so that's kind of the idea here. Okay, it's not too bad. Basically, the tricky part is finding mu, and then you got to find this antiderivative here, mu times g. All right, so let's try one more example. All right. So let's just double check. In this case, we have two different variables. We have r and theta. So r is our dependent variable, and theta is our independent. And so we see again, this is first order, okay, a first derivative, and r, nothing is nonlinear is happening to r. Okay, so we have a secant theta. Okay, but that's our independent variable, so that's okay. R is still linear. Okay, so this is linear first order. And we want to try and solve this differential equation. All right, so let's kind of do it the faster way. So we need to figure out what is, this is already in standard form because we see there's nothing outside in front of the dr d theta. Okay, there's only, our p in this case is secant theta. So p, I guess, is secant theta. And so we need to find an antiderivative of that, antiderivative of p of theta, d theta. Okay, which would be an antiderivative of secant of theta. Okay, does anyone remember what that antiderivative is? I forget, so I'm going to have to look it up. Let's see here. All right, this is one of the complicated ones. So in this case, it's antiderivative of secant. Yeah, somebody said it, I think. Yeah, let's see, it's the natural log of secant plus tangent. Secant theta plus tangent of theta, or tangent plus secant. All right. Good call. All right. So that's totally fine. Like, we don't expect you to have all those memorized. I mean, that's what tables of integrals are for. So look that up. And so that's actually really nice because that means this natural log, when I do the mu, our integrating factor, I have e to that. So I have e to the natural log, and that's going to cancel out. So obviously someone was thinking that when they created this problem. And so that e and the natural log cancel out. We're left with secant plus tangent. All right. So now kind of skipping and using that formula, like I said, we can solve for r. R is going to be 1 over that. So it's 1 over mu secant plus tangent times the antiderivative of mu, okay, secant plus tangent times g, in this case, which is cosine d theta. All right, so we need to do this antiderivative right here. So let's distribute the cosine. So we get secant times cosine. Okay, secant is 1 over cosine, so those will cancel out. We're just left with 1. And then we have tangent times cosine. Tangent is sine over cosine, so the cosines will cancel again. That's just going to be sine. So it's basically, this is a 1 plus sine. And so the antiderivative is just going to be the antiderivative of 1 is theta in this case, and the antiderivative of sine will be negative cosine. Okay, because if we take the derivative of cosine, the negative will switch it to positive sine. Okay, so we have theta minus cosine theta plus c plus a constant, all that, and then we still have this factor 1 over secant plus tangent. Okay, so that would be our full solution there for r. 1 over the integrating factor times this antiderivative here. Maybe you could do some more simplifying using some trig rules. I'm not sure, but I think this is plenty good for what we're doing here. Okay. Any questions so far on linear equations? It's pretty much just practicing finding these mu's and doing these antiderivatives here. Okay. All right. So like I said, if you're doing a problem in the real world and you remember this formula here, it's fine to just find mu and then skip right to this formula right here, 1 over mu antiderivative mu times g. But if you want to, it's also fine to kind of work it through step by step, recognizing we're undoing the product rule, taking the antiderivative to cancel the derivative out, and then dividing mu across. Okay, so either of those approaches is fine. All right. Okay, so let's talk a little bit about the next section as well. So section 2.4, we're talking about exact differential equations. Okay, so this looks a little different than what we're used to. Okay, because we have a dy and we have dx terms here. Okay, and looks a little funny. If these n's and m's have y's in them, these aren't necessarily linear. Okay, so these are sometimes nonlinear, which makes it kind of interesting. And so that's the idea of these problems. So in this case, we're actually working with what we call, instead of like a derivative, we're working with differentials. Okay, and that's a little confusing. So the idea is, if we have a function f, a 2D function, it's a function of x and y, and we do the differential of it, df, what does that turn into? That is basically the partial derivative of f with respect to x times dx plus the partial derivative of f with respect to y dy. Okay, so the differential is just kind of another calculus thing that we maybe are sometimes interested in. So we have like a 2D function. We do the differential and we can express it as like this partial derivatives. So if you're not familiar with partial derivatives, the partial derivative is basically a derivative with respect to one variable, and you treat all the other variables as constant. Okay, so if you've taken multivariable calculus, you should be familiar with that, but that's not necessarily a prereq for this course. So it's basically like a regular derivative, except that in this case, so like partial f, partial x, we would do the derivative with respect to x, but all the y's we would think of as constants. And the same with the partial f, partial y. You think of the x as constant, and you do the derivative with respect to y.
So is this different from a gradient? Did I miss that?
So a gradient it's related to a gradient. So a gradient would be a vector. So this would be like a gradient of f would be partial f, partial x, partial f, partial y. It would be in a vector. So this would be like some sort of like norm of the gradient, I guess. Like it's like the magnitude of the gradient in some sense. It's related to the gradient in a way. You could maybe think of it as it's also related to the divergence, okay, of f. So the divergence of f is partial f partial x plus partial f partial y. Okay. So that this is another function. So this is in some sense that we're leaving somehow like these infinitesimal derivatives in here, but it's somehow kind of related to these two ideas. So this is the divergence. So div. Sometimes you might write it as div f. And this is the gradient. Yeah. So it's kind of a weird way to write a differential equation. Basically, we have this 2D function f, and this differential here describes some curve along on that 2D surface. So if you can kind of think about, let me draw some rough sketch here. We have x and y axis. F will be in the z direction, so we have 2D, and it'll be some surface in that x and y plane. So F will be, maybe it's some weird kind of parabola type surface. The solution to this differential equation will be some sort of flat curve. So you can think about is some function where f of x comma y equals some constant c. So we pick a c and we set c to be 0. There's going to be some curve on this surface here that is where f equals c. Okay, and that curve is a solution to this differential equation, is the idea. So it's a little bit weird way to think about it, because we kind of somehow we're still doing like an ordinary differential equation, but we've actually gone to 2 dimensions in some sense. Does that make sense? Any other questions about kind of what we're trying to do here? One other thing to notice is that anything of this form is not necessarily an exact differential equation. Okay, it has to be. It's an exact differential equation when it satisfies something like this. And the way we know if it's satisfied, if there is an f that is like this, is when we can test it with this equation here. So we take the partial derivative of m with respect to y. If that equals the partial derivative of n with respect to x, then we know it's an exact differential equation. If this is not true, then it's not an exact differential equation. It's just some other differential equation. Okay, there is no f that satisfies this type of a differential equation right here. Okay. Basically, this is kind of, let me do a little side tangent here. That's related to the fact that partial f, the second partial x y equals the second partial of f with respect to y first then x. So it doesn't matter what you do, x or y first. If you do x then y or y then x, you should arrive at the same thing. And so this is m is like partial f partial x. And so then if we do the y derivative and then compare that to n with respect to the x derivative, that should be the same thing. Okay, because n is like partial f partial y. Okay, and if we do the x derivative, we should get this term right here. All right, so that's how we do it. So what we need to do is basically when you see something like this, you check it's exact by checking this equation. And then we're going to end up solving 2 other equations. We're trying to find f. And so we know 2 things. We know f, or partial f, partial x, is going to be equal to m, and partial f, partial y equals n. Okay, so we have 2 equations, and we can use these 2 equations to find f. Okay, that's the goal for exact differential equations. So let's do an example. Let's try and work through some of what that means exactly. So I've got an equation here. It's in differential form. We have dy and dx. Sometimes exact differential equations aren't always in differential form. You have to kind of rearrange them. Dx dy. That's kind of if you know it should be exact, you can. It's not too hard, but sometimes it's hard to spot those. So what we need to do, we need to check, this is m here, and this is n. We need to check that if this is exact or not. Okay, so that means that checking if the partial derivative of m with respect to y, does that equal the partial derivative of n with respect to x? Okay, so partial m, partial y. So we look here, x cubed, x is like a constant, so x cubed is a constant, that just goes away, that goes to 0. And then the partial of y, it's going to be 3y squared. Okay. That's partial m, partial y. Partial n, partial x, we treat y as a constant here. Okay, so it's basically just a constant times x. And so if we do the x derivative, we just leave the constant since there's only x to the first power. So it's going to again be 3y squared. All right, so those are equal. That's good. That checks. This is an exact differential equation. All right. So we know it's exact. Now we need to try and find that function f that satisfies this. That satisfies partial f, partial x equals x cubed plus y cubed, and partial f, partial y is 3x y squared. Okay, we need to find f that satisfies these two equations here. Okay, and we do that basically just by integrating. Okay, we see that if we want to cancel out this derivative here of f, we can just integrate both sides. So you can basically start with either equation. Okay, it doesn't matter which one you start with. So sometimes I try and pick whichever one I think might be easier to integrate. In this case, they're not really, neither is all that challenging. So let's just kind of do the first one here. So we integrate partial f, partial x with respect to x. That should equal the integral x cubed plus y cubed dx. Okay, that cancels. We're left with just f then. And now we do the antiderivative of this side. We use the power rule. So we would do, this would be x to the fourth times 1/4. And in this case, since we're integrating with respect to x, we treat y as just like a constant. So this is y cubed is just like a constant. This is just going to be y cubed times x. And then we need like we normally would have an extra constant here, but we think about y is also constant. So really what we have is some function y. So we really have a whole something else, g of y, left over. Because if I think about doing the partial derivative of this with respect to x, I'll get back to x cubed plus y cubed, and then anything that just depends on y is going to disappear. Okay, so I have some function here that maybe depends on y. Okay, so in order to find out what this g of y is, that's where I have to use the second equation. Okay, so I have this expression for f with respect to x and y, and I also know its partial derivative with respect to y. So let's do the partial derivative of this with respect to y and compare it to this term right here. Okay, so this, if I do the partial derivative of this term right here, that should equal 3xy squared. Okay, if this f are to be the same. Okay, so the partial derivative of that, so the x term, we treat as a constant when we do the partial derivative with respect to y, that just disappears. The y term, we have y cubed. We have to do power rule, so it's going to be 3y squared times x. We treat x just like a constant, so it hangs on. And then we're going to have g prime of y. Okay. Partial derivative with respect to y of g just depends on y, is just a regular derivative. All right, so that's partial f, partial y. All right, and so what should happen is you should get some terms that are the same. Okay, there should be some terms that are the same and some maybe that, and then whatever's left over here is what we're looking for g prime of y. So it turns out that 3y squared x, these are the same. So these we can subtract from each side, they go away. And so we have g prime of y equals 0. Okay, and so we want to find g. So in order to find g, we just take the derivative now of both sides, or the integral, sorry. we take the integral of both sides. So you integrate with respect to y, integrate with respect to y. The integral and the derivative cancel out, so we're left with g of y, and the antiderivative of 0 is just any constant. So this is going to be some sort of constant c here. All right. So what's our final answer? Let me probably need a note. So we know what g is now. It's just a constant. And so we know f then is going to be it's our 1/4 x to the 4th plus y cubed x plus g of y, which just is a constant, so plus c. And normally the way we write this as we want to write this as this is really is like a in this form it's still a kind of a 2D thing. It depends on x and y. But really we're looking for that curve. And so you really it's the curve where this equals 0 generally. Or you could rewrite it, bring the constant over, it's really 1/4 x to the 4th plus y cubed x equals a constant. Okay, this curve here, this implicit curve, is a solution to our differential equation that we started out with. Okay, so that's why it's still kind of an ordinary differential equation, because we're looking we found this implicit solution curve to this differential equation. Okay, but somehow we're kind of thinking about it at a higher dimension, 2 dimensions. But really, our solution is still one-dimensional. All right. So to kind of wrap things up, let's just try one more example of the exact equation.
A question for you there.
Sure. What's up?
Yeah. So when you took that partial f partial x dx and integrated on both sides, yeah, right there. Could you equally have done partial f partial y dy and then integrated the other part of the?
Yep, exactly. So you could have done that, and you would have ended up with something, and then you had a constant g of x.
Right.
And then in order to find g of x, you would have taken a partial with respect to x and compared it to this equation here.
Gotcha. Okay. And all things going well, we would have come to the same solution.
You would have came to the same solution.
Awesome.
Yes. Okay. One thing I see sometimes in this class is you could just, which is kind of, it works, but it is a little. You could just do both of them. So you could do like integrate m with respect to x, and then you could have done the other one, integrate this with respect to y. Okay, and you end up with a whole bunch of things added together. And then you compare those two things, and you see some of them are the same. So you leave out the doubles and include everything once, and you should find f that way. So that's one other kind of way to think about it. So like if I had done partial f partial y, I would have ended up integrated that. I would have ended up with this y cubed x term plus c. Right, and I did the other one. I would have ended up with the same thing, the y cubed x plus 1/4 x to the 4th. And so you just make sure you include each term once. But I think that's kind of confusing, so that's why I say do it this way. That makes sense? So let's try one more example and see if that clears things up. So in this case, we have another one in differential form. Just mark here. So this is m, this is n. We want to check it's exact. So I need to take partial m with respect to y. Okay, so it's the opposite of whatever this is, the dx. So we're going to take respect with y. We'll have to use chain rule, so that's going to be like 2x plus y times the root of the inside, which is just 1. Okay? And then we do the partial n, partial y. We treat x as a constant. So that just turns into y. Or treat, x as a constant. sorry, with respect to x, I wrote that wrong. Partial n, partial x. So we treat y as a constant. Okay, so that first term, the x is like 2y times x. 2y is a constant, and so the x just goes away. Plus derivative of x squared is going to be 2x. And then the 1 is a constant, so that just goes away. So again, we see the same thing. We have 2x, 2y. Those are the same, so it is exact. Right? So we have our two equations now. We know that the partial of f with respect to x equals x plus y squared. And the partial of f, partial of y, is this other term here. So it's 2xy plus x squared minus 1. All right, so let's do the opposite way this time. Let's integrate the partial f, partial y. So we're trying to solve for f. So we do the integral of partial f, partial y with respect to y. That should be the integral of 2xy plus x squared minus 1 with respect to y. Okay. So we see that canceled out, which we have f 2xy. So treating x as a constant. So it's like y. Use the power rule, so I'll turn into y squared. Divided by the 2, we just get x. X squared is like a constant, so that's just x squared y. Negative 1 is a constant, that's minus 1, minus 1y. And then we're going to have some other thing that's a function of x. All right, because this is a partial derivative, anything with just respect to x would have got canceled out. Okay, so the unknown constant is actually a function of x in this case. All right, so in order to figure out what that is, we need to take the partial of this term with respect to x. And we can compare that back up here to x plus y quantity squared. So we do that with respect to x. We get y squared, x squared y. So that'll be, bring the 2 down, that'll be 2xy. The negative 1y will go away because it's just a constant. Y is treated like a constant. And then g of x should be g prime of x. All right, and we know that whole thing should be equal to x plus y squared. Okay, based on our other equation right here. So we now solve for g, and then we'll have our full solution for f here. All right, so what we know is if we have to kind of distribute this squared here and FOIL that out. So let me just rewrite this. We have y squared plus 2xy plus g prime of x equals, so you have x times x, you have x squared, and then we have a cross term, so it's going to be 2xy plus y squared. All right. So we see the y squared and the y squared are going to cancel. 2xy will cancel. And we're just left with g prime of x equals x squared. Okay, so to find g, we just have to integrate both sides with respect to x. So we integrate that. That should be the integral of x squared with respect to x. Okay, simple power rule again. 1/3 x cubed plus a constant. Okay, and this will be equal to g of x. So one thing to kind of point out is because in this case g is only a function of x, and so we're not dealing with any partial derivatives here, and that's why this is only a constant and not some function of y. Okay, because now that we're only dealing with regular derivatives, when we do the antiderivative, the constant is a constant. Okay, whereas before, when I did it up here, I'm dealing with partial derivatives, and so when I undo it with an antiderivative, the constant is some function of all the other variables besides the partial derivative, besides this here. In this case, it's just x. Okay, so if you had like a three-dimensional function, x, y, and z, and then you undid a partial derivative with respect to y, this would be a function of x and z. Okay. And so that's the difference here, getting some sort of function instead of just a regular constant here. Okay, but that tells us what g is, and that basically that helps us solve it. So that means that f is xy squared plus x squared y minus y plus g 1/3 x cubed plus a constant. Or really what we think about our solution is xy squared plus x squared y minus y plus 1/3 x cubed equals c. Okay, it's this curve on the surface of f. Okay. And in this case, I actually had an initial condition, so I didn't mention that. So we have in order to find which curve specifically we're looking at here, we know that y of 1 equals 1. So that means that when x is 1, y is also 1. So if we plug in 1 for x and y, we can find out what the c specifically is for this initial condition here. Okay. So this turns into 1 times 1 is 1, plus 1, minus 1, plus a third, equals c. So 1 minus 1 cancel. We're left with 1 plus a third, so 4/3. C should be equal to 4/3. All right, so that's the really f x y equals 4/3 is the solution. Okay, with what our solution for f is previously. Okay, so that's the solution to the initial value of problem. Okay, it's a particular solution, not a general solution. All right. So any other questions about exact equations or questions in general?
Sorry, I think I missed this. When you're plugging in the initial conditions, what did you plug in for? Yeah.
So yeah, sorry, I was a little off the screen. So we knew that, so the initial conditions are given to us as y of 1 equals 1. And so what that really means is that x equals 1 and y equals 1. Right? Y of 1 equals 1. So x equals 1 and then y equals 1. So everywhere here, I plugged in 1 for x and 1 for y. So that's 1 times 1 is 1, plus 1 times 1 is 1. And then we have a minus 1, and then this is turned into a 1/3. And that equals our constant here. So this is the normal way to, the standard way to write the solutions to these equations is something like, it's like our function f equals a constant here. Okay, so in some ways you could move the constant and you could say equals 0. That's also a valid way to write it. It's just this is convention. And so because I wrote it this way, then I plugged in my conditions for x and y, and I could solve for c. And so then if you were really going to write the particular solution, I probably should really write out this whole thing here equals 4/3. xy squared plus x squared y minus y plus a third x cubed equals 4/3. That's some curve in space that satisfies the differential equation. It satisfies this differential equation and this initial condition. That answer your question?
Yeah, it does. Thanks.
Yeah, so it's actually it's not too, this is not necessarily, I don't think, too hard to do. I mean, it's just you're just doing integrals and canceling out derivatives like we've been doing. But these exact equations are interesting because in some ways if we're just given an equation like this, we're somehow kind of like inventing this 2D function f and then finding a curve on its surface that satisfies this differential equation. So it's kind of somehow we're like going up one dimension in order to solve these 1D equations here. So it's hard to think about, but if you just kind of focus on these partial derivatives and undoing them, it's not too bad. All right, well, any other questions before we wrap it up for the day? All right, sounds good. I hope you guys hear my dog barking in the background. Hopefully not too bad. Anyways, all right, well, have a good rest of your week. I'll see you guys next week, and you'll see Jasmine on Thursday. So hope you have a good rest of your day.